Have you ever been in a super tall skyscraper, looked out the window, and thought, wow, I am really, really high up? And then you realize the only thing between you and a very long drop is a metal box hanging by a few cables. It sounds a little scary when you put it that way, doesn't it? But here's the thing, elevators are actually one of the safest forms of transportation in the world. So, how exactly do these marvels of engineering lift us up and down, day in and day out, without a hitch? Today, we're going to pull back the curtain and dive deep into the fascinating world of elevators. Let's start with the most common type you'll encounter, the traction elevator. Imagine a giant, super strong seesaw. On one side, you have the elevator car, which is what you ride in. On the other side, you have something called a counterweight. This counterweight is crucial. It weighs about the same as the elevator car when it's 40 to 50% full. So, if the car is carrying a few people, it's pretty much balanced with the counterweight. Now, where does the seesaw part come in? Both the car and the counterweight are attached to incredibly strong steel cables. These aren't just any ropes, they're bundles of steel wires twisted together, making them ridiculously durable. Each cable alone can support the weight of a fully loaded car, and modern elevators use anywhere from 4 to 8 of them. These cables loop over a large pulley at the top of the elevator shaft, called a sheave. The sheave has grooves that grip the cables, kind of like the tread on your tires gripping the road. This sheave is connected to a powerful electric motor. Here's where the magic happens. When you press a button, the motor turns the sheave. Because the car and counterweight are balanced, the motor doesn't have to lift the entire weight of the car. It just needs to give a little nudge to tip the balance. If the car needs to go up, the motor turns the sheave, pulling the car up and letting the counterweight go down. If the car needs to go down, the motor turns the sheave in the opposite direction, letting the car's own weight, with a little help from gravity, lower it down while the counterweight goes up. This system is incredibly energy efficient. Think about it, instead of lifting thousands of pounds from a dead stop, the motor is mostly just overcoming friction and the small difference in weight between the car and the counterweight. It is like having a friend help you lift something heavy. It makes the job a whole lot easier. This is why traction elevators are perfect for tall buildings, where efficiency is key. But what about the ride itself? You don't just want to be yanked up and down. You want a smooth journey. This is where guide rails come in. Along the sides of the elevator shaft, there are 2 vertical steel tracks. The elevator car and the counterweight both have guide shoes or rollers that fit snugly onto these rails. This ensures they travel perfectly straight up and down, without swaying or bumping into the walls of the shaft. It's like a train on a vertical track. So, we've got the lift, we've got the smooth ride, but what about the most important part, safety? This is where elevators truly shine. The genius of elevator safety dates back to the 1850s with a man named Elisha Otis. He invented a safety brake that revolutionized the industry. Modern elevators use an evolution of his concept. First, there are the multiple cables. The chance of all of them snapping at the same time is astronomically low. It's just not something that happens. But, let's play a what-if game. What if the impossible happened and the cables did fail? That's where the primary safety system kicks in. Attached to the elevator car is a device called a governor. This is a separate pulley system with its own cable, connected directly to the car. As the car moves up and down at a normal speed, the governor spins along happily. But if the car suddenly starts to fall too fast, the governor spins so quickly that centrifugal force causes a pair of flyweights to swing outwards. These flyweights then trip a switch, which does 2 things almost instantly. First, it cuts the power to the motor, so it stops trying to turn the sheave. Second, and most importantly, it activates the safety brakes on the car itself. These aren't like your car's brakes. They are powerful, wedge-shaped clamps that are forced into a notched or serrated part of the guide rails. Imagine a powerful jaw chomping down on the steel rail. The friction is immense, and it brings the elevator car to a screeching, but safe, stop within just a few feet. So, Even in a free fall scenario, the car wouldn't plummet to the bottom. It would be caught. But the safety features don't stop there. What if the elevator just goes a little too fast, but not fast enough to trigger the main safety brake? There are speed sensors that will slow the car down. What if the elevator tries to go past the top or bottom floor? There are limit switches in the shaft that will cut the power and stop the car. What about the doors? Elevators have sensors, either a mechanical edge or an infrared light curtain, to make sure the doors don't close on you. The car won't even move unless all doors, both on the car and on the floor landing, are completely closed and locked. It's a system of redundancies built on top of redundancies. Now, not all elevators use the traction system. For shorter buildings, typically 6 stories or less, you might find a hydraulic elevator. These work on a completely different principle. Instead of cables and counterweights, a hydraulic elevator is basically a giant piston pushing the car up. Imagine a large cylinder buried in the ground directly beneath the elevator shaft. Inside this cylinder is a piston, which is connected to the bottom of the elevator car. A pumping system forces a special oil-based fluid from a reservoir into the cylinder. As more fluid is pumped in, the pressure builds, pushing the piston up and lifting the elevator car with it. It's like a superpowered car jack. To go down, the system simply opens a valve. The weight of the car, along with gravity, pushes down on the piston, which forces the fluid back out of the cylinder and into the reservoir. The descent is controlled and smooth because the valve can be opened slowly or quickly. Hydraulic elevators are simpler in design and generally cheaper to install than traction elevators. However, they are less energy efficient because the pump has to do all the work of lifting the full weight of the car and its passengers every single time. There's no counterweight to help out. They are also slower and have height limitations because you need to dig a hole deep enough for the cylinder to retract into. That's why you don't see them in skyscrapers. Finally, let's talk about the brains of the operation, the control system. In the old days, elevators had human operators who would manually control the speed and stop at each floor. Today, it's all computerized. When you press a button, you're not just closing a circuit. You're sending a signal to the elevator's central computer. This brain is a sophisticated piece of technology that manages everything. It keeps track of where the car is, which floor buttons have been pressed inside the car, and which call buttons have been pressed in the hallways. It then uses complex algorithms to determine the most efficient way to serve all those requests. Have you ever been in a busy building with multiple elevators and noticed how they seem to work together? That's the group dispatching system. It sends the closest car to you, minimizes wait times, and groups passengers going in the same direction to save energy. It's a constant, high-speed game of Tetris, optimizing the movement of all the cars in the building. The control system also monitors all the safety features constantly. It's checking the door sensors, the speed governor, the motor temperature, and hundreds of other parameters every fraction of a second. If it detects even a minor issue, it can put the elevator into a safe mode or take it out of service and call for a technician. So, the next time you step into an elevator, take a moment to appreciate the incredible engineering at work. From the simple but brilliant balance of the counterweight system and the powerful grip of the safety brakes to the silent, efficient brains of the control system, it has a symphony of physics and technology designed with one primary goal: to move you safely and reliably. That little metal box is far more than just a box on a string. It's a testament to over 150 years of innovation, making our modern, vertical cities possible. Thanks so much for watching. If you found this interesting, be sure to hit that like button and subscribe for more deep dives into the technology that shapes our world. See you next time.